Yes, good evening, everyone. This is the first webinar as the Civil Engineering Sectional Committee of ISL. As well, this is a joint webinar with the American Society of Civil Engineers Sri Lanka section. And I would like to invite Engineer Mrs. Kamala Gunawardena to give a brief introduction about our resource person. Thank you.
Yeah, thank you, Inje Banduga. Thank you for your comparing today. Welcome speech is, I think this is the second one I'm doing it for Dr. Nihal. Good evening, ladies and gentlemen. It is my great pleasure and privilege to deliver these opening remarks and extend a very warm welcome to all of you joining us this evening for this webinar, organized as part of the knowledge sharing session of the Civil Engineering Sectional Committee. So we are joining with the American Society of Civil Engineers. Jointly, we are doing it today. First and foremost, I would like to extend a special welcome to our esteemed resource person for today's session, Engineer Dr. Nihal Vitarana, who will be sharing his expertise on the highly relevant and fantastic topic, design against ambient thermal effects on concrete. I would also like to warmly welcome all participants who have joined us online today. Your presence and active engagement are what truly make this session meaningful. We look forward to your participation, questions, and discussions, which will undoubtedly add great value to this knowledge sharing platform. Before we begin the technical sessions, it's my pleasure to briefly introduce our distinguished speaker. This is, in fact, the second occasion, as I mentioned before, and had the honor of introducing at this forum, having previously done so during my tenure as chair of the Civil Engineering Sectional Committee 3 years before. Dr. Vitar is a graduate from the University of Moratuwa and holds a PhD in Structural Engineering from University of Canterbury, New Zealand. He also possesses a master's degree in geotechnical engineering from the University of Sydney and MBA from Deakin University. With over 4 decades of consultancy experience, Dr. Vitarn has made outstanding contributions to both the technical and management aspects of engineering practice. He is currently an independent consultant involved in critical infrastructure projects in the water, energy, and transport sectors. Dr. Vitarn has also carried out pioneering research on the thermal behavior of concrete structures and has served on the technical committees of ASCE 3735 and NECD 3206, providing valuable input in both thermal and seismic design aspects. On behalf of Engineer Madhushankar, Chairman of the Civil Engineering Sectional Committee and the National American Society of Civil Engineers Sri Lanka chapter, I wish to express our sincere appreciation to Dr. Vitarn for generously sharing your knowledge and experience with our members this evening. Once again, a very warm welcome to all the participants. We trust that this session will provide valuable insights and help address many of the practical challenges you encounter in your professional work. Without further ado, I now invite Dr. Nihal Vitharan to commence this session. Thank you.
Thank you,
Thanks,
madam.
Kamala, for the generous introduction. And of
also,
course,
Dr. Kamal Laksri, sir, if you want to add something, yeah.
Okay. Kamal was here a few minutes ago.
He's done, I think.
Maybe, yeah. You can continue, sir. Okay.
So, thanks, Kamala, for the generous introduction, and Danuka for organizing it. Banduka, please, you need to run the slides, but under no circumstances, please don't give it to share it. Hackers are waiting. Last time we had bad issues.
Sure, sir.
Okay, now getting back to this one, Dr. Kamal Laksri and Manduka, contacted me about a week ago and said, Nihal, we need to give another technical talk because they don't have many people to speak at this what you call weekly or monthly seminar. I said, I will do one. But it is normally 11 o'clock in Sydney time by the time I finish. I have done about 8, I think. So my wife said, you are crazy, that means you are a piece. Anyway, so this is a very unusual loading condition, and most engineers get it wrong, either too conservative or too risky. When I said risky, if a water retaining structure cracks, in where I work, ANZ and other parts of the world, the client will sue the consultant. You can't offload it to somebody else like, we didn't know that it is going to rain, so flood is not our issue, or we didn't even listen to the BBC news. We can't find those excuses here. So I have done a lot of litigation issues with lawyers where thermal effects have caused cracking of many structures, leading to big disputes, because normally a water retaining structure, so desalination plant has a 120-year design life. So if the structure crack within sometime 2 to 3 months since construction, that's a problem. So I think you may know more than I do, but this is how we do it in Australia, New Zealand, and our standards are being adopted in North America, such as Canada as well. Next slide, please. Next slide. Yeah, so my relevant background, I have about 40 years of experience in the industry, always in consulting. I never taught at the university. And I did my PhD about 35 years ago on strain-induced stressing of concrete storage tanks, where thermal effects and seismic are the key issues at University of Canterbury. And served on 2 technical committees, ASCE 3735, that is our concrete liquid retaining structures, New Zealand 3106, that's New Zealand water retaining structure standards. And also I had served on ASCE 3600, that is concrete code, and NCOLD, Committee on Concrete Dams and Earthquakes. Now, over the years, still I'm learning on thermal issues and diffusion and cracking. A lot of things now I get involved are when things go bad, or what we call belly up. I think in Sinhala, Walakajo, or whatever, kick the bucket, Korea. So many things, projects can go wrong. And then client doesn't want to accept the design. And most of our designs are either alliance, where everybody take the risk, or D&C, design and construct, where the contractor take the risk. And contractor take the risk is a consultant do a bad design, money coming out of contractor's bucket. And next one, please. This is just to get into the real problem. What you see is a concrete tank. It could be a concrete tank or a sludge sewerage digester, where the solar radiation incidenting on the external surface, while internal phase retains retain the temperature of the water or sludge. As it is a big thermal mass, it remains constant. So this set up a very transient or peaky thermal gradient. If the wall is thinner, as you can see, temperature distribution would almost be linear. But if it is thicker, it will be highly nonlinear. I will discuss both things during this webinar. And one of the critical things with design against strain-induced loading is a imposed deformation. And most universities don't teach that either. Either professors are busy with their consulting, or they find it too hard to learn themselves as well. And that's a problem throughout the industry, even now, when it comes to shrinkage, swelling, temperature, engineers don't know how to do it. They probably follow deemed to satisfy criteria. Probably Sri Lanka follows the British standard. I think they allow for nominal reinforcement or nominal temperature. That is not good enough because the solar radiation varies from place to place. Like we had 46 degrees in Sydney yesterday, whereas some part of the world it could be minus 30. So it cannot be applied like deemed to satisfy like panacea or what is called in Sinhala kokadattaira. It doesn't work that way. So you have to be aware of what you are doing, and design against strain-induced loadings are much more difficult than design against applied loading as live or dead loads. Next one, please. Now, this is unlike any other standard in the world. New Zealand and Australian standard, we give this temperature distribution, which needs to be satisfied by the engineers as a minimum. Our standards are not legally binding, so the engineers have their own duty of care. So, but they say this is a minimum against which you need to design your structures. Now, what you can see on the left is tank full and right is tank empty. When tank full, in the summer, external temperature can go up by 30 centigrade compared with the internal. When it in the winter, like New Zealand, it can go up down to minus 20, while inside this at the water temperature. When tank is empty, it's not that severe because inside the tank getting heated up too. So the differential is much less. Now, if we just to get our minds in order, if I look at 30 degrees centigrade, if I restrain a concrete member from expanding with Young's modulus, say 30,000 MPa, that is equal to 9 MPa compression or tension on the other side. If we are designing a pre-stressed tank, very difficult to satisfy that criteria. That's what smartness plays because you need pre-stressing becomes uneconomical after about 6 MPa. So these are the two gradients which we have given. As I said earlier, these are valid only for wall thicknesses less than 200 millimeters. Anything greater, they will become nonlinear. But code doesn't provide any guidance. Designers have to do it themselves, and most designers pretend they didn't see that commentary or limitation in the standard. Let's go to the next one, please. Yeah. Don't think water retaining structures is innovation and guys didn't have anything else to do in the life, so they put these two gradients. If you look at the bridge, this is a paper I presented somewhere in Japan, in Sapporo in 1995. If you look at a concrete bridge standard, you can see pre-1969 is uniform. So if it is a simply multi-span bridge on elastomeric bearings, it will expand and contract, so no bending moment of axial, but it develops. Now what we got is a fifth order parabola. If we apply this gradient to the pre-stressed concrete bridge design, this will dominate the live load and the dead loads. That's what it is, becomes very critical. You look at the temperature loads very carefully. This is going to be dominant more than the dead and the live load. I don't know whether Sri Lankan standards or British has anything, and European standards have. This is introduced by the New Zealand Ministry of Works. As a graduate, I took measurements on the temperature gradient. Probably I got paid about $1 an hour, which is worse than what a slave would get those days. Next one, please. And yeah, it's a slide is too small, the figure. The top one, this is a circular tank, just to show the dominance of thermal loading. circular tank. Top ones are the hoop, circumferential and vertical moment due to hydrostatic load. Then bottom two are I think the top one is a tank full, applying the gradients given in the standard. They are much higher than that of the dead and the hydrostatic loading. So if somebody designing as per our standard, this is a norm. The thermal loading is much higher than that from the hydrostat loading. Next one, please. And this is what most engineers forget or haven't understood, including the professors. Thermal loading is a serviceability loading only. It doesn't apply to ultimate limit states unless there is a secondary effects like buckling. It's normally very difficult to buckle a bridge or water tank. The diagram shows at serviceability, you can see in the same deformation, the serviceability, we get a higher force on the y-axis, but when it is at ultimate, because already in the plastic stage, that imposed deformation doesn't give an increase in the ultimate load. So it is wrong and unethical to do the design of any structure, concrete structure at ultimate state, taking temperature gradients into account. We don't do that. Code implicitly states that too, but there are engineers who apply this to ultimate limit state and end up with reinforcement cages so congested even a bumblebee can't go through. That gives a lot of problems with concrete because you end up with honeycomb concrete. It is because they don't follow this the basic principles properly. Next one, please. Now, as I said, those linear gradients are easy to apply to any design because linear gradients, we break that into uniform, average, and differential, and there are charts available to determine the bending moment and the axial forces. But when the members become thicker, more than 200, the temperature gradient is extremely nonlinear. That means the design effort need is a little bit more complex. And we had to determine I will show you later, primary stresses. That is, if the member is unrestrained, what are the stresses developing? Because it violates plane section remain plane hypothesis. Next one, please. Yeah, so this is typical temperature distribution in a hydrating world, not solar radiation. We get higher temperature in the middle and lower one on the sides because formwork, normally steel, is more conductive than wood formwork. So that bottom two, we have broken that into primary and secondary stresses. The one on our left, when we look at it, are the primary stress, unrestrained. So we get primary stresses. They are self-equilibrating. And then if it is fully restrained, we get the shape on the right side.
Huh.
So that's what I said. We had to be very careful when we dealing with nonlinear temperature gradients. Next one, please. So I just put this is on one of the papers. I can send it to Bandhu can get it. These are the simple equation on a beam type member under both external and internal restraints. If RF is external restraint and RM as restraint against bending moment. So if we put RM and RF 0, it gives primary stresses. If we put RM and RF equal to 1, you get the fully restrained conditions. And once we know once we separate out the primary stresses, linear gradients, there are charts available which designers can do. New Zealand 3106 has charts for circular tanks, and one of my early work got charts for the rectangular tank with sun on any of the four sides. So the life is much easier when things are temperature gradients are linear. Next one, please. Sorry, I had to rush through it's a little bit complicated subject, but just trying to give you an insight into what is there. Yeah, so as I said earlier, this is how a nonlinear temperature distribution on the left has been broken down to uniform, average, differential, and primary. So first two, uniform and differential, very easy to deal with. There are charts for the water rating design engineers. Next one, please. So when we, again, like what you saw earlier on the New Zealand temperature gradients, we got a 0 to 30. So we broke it down to 15 uniform and 15 differential. So those two can be easily used in any of the charts available. Uniform, as I said, if you got a rectangular tank with uniform temperature drop, you get very high axial forces. That's what most, if not properly designed, rectangular tanks tend to crack vertically along the length. Next one, please. Now, I don't do much research or that sort of things. Currently, I'm busy earning money. That's the target. But about a year ago, a Sydney client came and said, Nihal, we have a problem. I said, what's your problem? Designers come with crazy design, a lot of reinforcement. We have never seen that many reinforcement in tanks, and still they crack. So would you mind looking at this nonlinear temperature gradients for our tanks and the digesters? So they had a large portfolio of water tanks and digesters, and some information during the operation of these are available with respect to temperature. So water tanks, we consider thickness at 250, 450, 600, 700, and digesters, very similar, but slight change in the thickness. When I said APD, I'm not a process engineer. They are called acid phase digesters. GPD is gas phase digest. They are not exothermic. That means they don't produce heat when the sludge is digesting. But when you look at APD, acid phase, they put raw sewer into them. But when it comes to GPD, the sewer is heated at 36 degrees throughout its decaying process. So we can't just take water tank temperature gradients and put it to a digester. That's the problem. Yeah, next one, please. As I said, temperature gradients were first introduced, I think introduced in a person called Ackerman in South Africa. He found a lot of tanks crack, and then he found out that it is due to temperature changes in South Africa. He published a paper in Institute of Civil Engineers in 1960. Then Wood, he was the head of structures at Ministry of Works, New Zealand, measured temperature development in a pre-stress wall in Wellington, 178 millimeter thick. Those are the measured gradients. And the New Zealand was lucky because New Zealand government put a lot of money into research those days. I was lucky too. I was there 85 to 1995, all funded by the New Zealand government when it comes to concrete and earthquakes. Next one, please. Then 1977, again in New Zealand, late Professor Priestley measured and calculated things on a 200 millimeter thick wall. Nigel was my PhD supervisor at Canterbury. So you can see even with 200 millimeter, there is a nonlinearity, but the code writers, we didn't want to make engineers running away from the standards when they look at nonlinear gradients and don't know how to design it. So we simplified it by linearizing, but again, if they apply that to thicker members, design becomes very uneconomical. Yeah, next one, please. As I said, similar thing. Then there's what I didn't want to make things complicated. When it comes to strain-induced loading, they are deformation dependent, or modulus EI is Young's modulus, I is the inertia dependent. Similarly, if you take something expanding steel bar, if you restrain it, the induced force is proportional to the A and axial area and the E. So cracking of reinforced concrete relaxes the induced forces. That's what we call strength stiffness reduction factor, RF, in the standards, and it only goes up to 250. So gradient, use those ones are used cursorily by engineers for, just like anything. 600, they use that and come up with tons of steel, and contractors nearly go bankrupt. And even if they don't go bankrupt, when it congested steel cause honeycombing, they probably will go bankrupt again. Yeah, next one, please. Yeah, so what I'm going to present here is just give a little bit introduction to how to do the solar radiation estimating from basic grade astronomy, and then how to include that in a finite difference program, which I wrote some 40 years ago. Now you can do it in Excel spreadsheets using circular referencing to determine nonlinear temperature gradients through walls, any wall. Yeah. So the temperature gradient assessment needs some key input parameter. Of course, solar radiation. Then ambient temperature. If ambient temperature increases, it set up a temperature gradient as well. Inside temperature, as I said, gas phase digester, the artificial heat to 36 degrees, whereas a concrete tank in Australia, even in summer, temperature would be about maximum 18 degrees. Then wind speed, higher the wind speed is it take away heat from the heating up wall due to the wind. It's called convection. Then thermal properties, concrete and surface absorptivity. Because if it is a dark surface, black, absorption coefficient is about 0.9. If it is white, it's 0.35. So if you can afford to paint the walls in white color, either reflective sheets, it will set the temperature gradient lower. Such things have been done in the past and even nowadays, but it's a very costly experience. Costly exercise. Yeah, next one, please. Yeah, I am not a astrology or astronomy, but there are good things available on the internet from the solar panel industry or solar energy, where you can learn the basic things from the movement of the sun. Now, with this model, what I am saying, we need only one solar energy parameter, which is the total solar energy on a day on a horizontal surface. That is reported by the Bureau of Meteorology, Australia, online. I'm pretty sure it may be in Sri Lanka too, but having seen recent flood events, I don't know whether even they have seen where the sun is rising or setting. That is available. So with that parameter, and given the latitude of a place, like latitude here is at minus 33.53 with respect to the equator, on a given day, the solar radiant intensity, that's how it varies from sunset to sunrise, can be calculated. I use a spreadsheet, but it involves a lot of mathematics. Somebody told me there are programs, but with program they are not very flexible. So this is what it is. North, sunrise probably doesn't need to be exactly east and sitting on the west. Now, when sun is just above the north, that is at the highest elevation, altitude, and that is the time the solar radiation intensity is the highest. Yeah, next one, please. Yeah, this is the definition. The sun is there, and when you project it to a horizontal one from the northern bearing, you get azimuth, which is A, and elevation is theta. These can be calculated for a given day based on equations. And normally what called TS is solar day. That's the time difference between sunset and sunrise. Each hour, sun moves by 15 degrees. So that's that's how it works. So if you know the solar day, you can calculate solar angle by dividing by 15. Yeah, next one, please. Yeah, this is basically what happens, why we get summer, winter, because some reason, don't ask me why, Earth doesn't rotate in line with the center line of the sun and the Earth. It had got an angle called declination, and it changes throughout the year. So when the Earth rotates around, the orbits around the sun, it is at a varying, this awkward angle, declination angle. That can be determined given the day. There's a formula to determine that. So as I said, total global solar radiation Q, normally megajoules per meter squared, the key parameter need to run this model. Yeah, it's called cumulative, and I'll show you how there's a formula to calculate on hourly basis. So it's on a horizontal surface. So, but if we hold a paper perpendicular to sun rays, that's called direct beams radiation. But and a vertical surface, solar radiation is much different than from horizontal, because vertical itself is at an angle. So there's direct beam got two resolutions to be. First, we had to did from the horizontal beam, we had to go to the vertical direct beam and then convert it back to the bearing of the wall. Yeah. So anyway, as I said earlier, at solar noon, sun is at the highest elevation, which is the altitude. There are few methods available to convert that, I said, daily one to hourly. Glowin, I think he's a Scottish, he introduced his model in somewhere in, I can't remember, 1970s, and that is the credible model used throughout the world. But people do minor variations and say that it is their model is the best, but human always have an ego, so that's what it is. Now, we don't have any problem. I can just hit the button and get any previous days, what's the total global solar radiation. That's the equation. IT gives the joules per meter squared per second on a horizontal surface. Q is the total global radiation in a day, and DS is the solar day. You can calculate mathematically from formulas. Yeah, next one, please. Now, again, a little bit astronomy. When we get solar radiation on horizontal surface, it got two components. One is, as I said, direct beam, and when the sun emits its energy, when it enters Earth's atmosphere, it gets scattered too, known as diffuse. It's like you got lights on half of the Earth, which is on the hemisphere. So all that hemisphere bulbs putting solar radiation on the horizontal point. But when it is a wall, only we get half of that one, because it's a quarter of the Earth. So we need to first, once we determine radiation intensity or horizontal, then we had to determine what's the direct component and what is the diffusing or the scattered component. And again, it is going to solar energy. I think some Australians who use scientists work at CSIRO develop a methodology how to separate those things out mathematically. Next one, please. I use the Australian. Yeah, so Spencer is an Australian scientist at CSIR use his method and then compared with another person's method. So they gave, you can't get 100% accuracy, but the solar energy estimates science with least precision. So you should not try to get the number to the third decimal place. One other thing with the vertical wall is we get reflection back from the surrounding. So if it's a clear surrounding with a lot of white buildings, in New Zealand, when they measured at the Christchurch airport on vertical panels, they found 40% coming back from the near other surrounding structures. So up to what you measured on a horizontal can go up to by about 40% on a vertical wall because of the reflection back from the surrounding. Yeah, next one. Yeah, this is sort of, I put this one, how to, you got a vertical wall at an angle F to the north, and then the sun azimuth and the altitude. So it's not complicated mathematics, but just need to resolve direct beam and diffusion in different angles. Next one, please. Yeah. In a simplified case, that's the equation given one on a vertical wall. Once we know what is the thing on the horizontal surface, IHT, because it has the bearings and the azimuth involved. Yeah, next one, please. I'm just giving insight. It's so that you know what's in. Yeah, this is all that method. Then I applied for the maximum daily. We had now data on the daily total since 1980, so it's nearly 45 years data. And out of that day, 3rd of January 2000, we had the highest solar radiation in Sydney. That is 35 megajoules per meter squared, maximum ever recorded since 1980. Then use that sole number to develop solar radiation intensity on vertical walls facing east, west, north, south. Again, it's not clear. So you can see the one big curve is the one on the horizontal surface, and then the two ones on the sides are the east and west, because on the west facing wall things getting peaky in the afternoon compared with that one on the east get in the morning. Yeah, next one, please. One other input parameter we need, that's ambient temperature. Again, now this is a trick. I don't know what is reported in Sri Lanka by the Department of Meteorology. Here, they give Tmax, maximum ambient temperature in a given day, and the T minimum. So it's variation, hourly variation, we had developed a curve. There are a few models, and that's what I have done here. So we get Tmax, T minimum given in the standards, and then convert it to hourly, because we need ambient temperature. As I said, convection. If ambient temperature is lower than the surface temperature of the concrete, heat will be lost to the surrounding due to the convection. If it is windy day, more heat will be lost. So that's what we need, that T80 in that equation. Next one, please. Next one. Yeah, so there are two models available normally engineers use and on bridge temperature calculations. Fu is I think from Hong Kong. Hers is a professor who used to work at Adelaide University in South Australia. They both give very similar curves, but Fu's one is better because it's a simple formula. So only two parameters we need is Tmax and Tmin. On this one, the assumption made is minimum mean lowest temperature at 3 a.m. in the morning and the highest at 3 p.m. in the afternoon, and sudden drop of 2 degrees at sunset. Yeah. Next one, please. Yeah, so this is a comparison with measured ambient temperature. 4th January 2020, where measured temperature was 45 degrees. At which, yeah, so while T minimum on that day is quite unusual day, minus 3.3. Sorry, maximum was measured on 4th of January 2020, 45, and winter T minimum occurred on the 16th July 2008. You can see the two models versus measured are reasonably accurate, not accurate, reasonably good. You can't get accuracy on these ones because I said this is not a precise science. Yeah, next one, please. Yeah, so that's the minimum temperature day. It's reasonably accurate as well. Yeah, next one. Next one. Now the other one thing we need to do, what's the inside temperature of the water or the sludge? It's very difficult to do any mathematical predictions because operational water comes and goes depending on the demand. Similar with sludge. Sludge will be exposed to atmosphere before it is fed into the digester. Then after phase 1 digester, it goes to the phase 2 digester. So the best thing is to have some sort of calibration of inside temperature with a parameter. Best parameter is the ambient because water is coming from a dam or somewhere or pipeline. And previous, like in New Zealand, they assumed that inside temperature is always equal to the 6 a.m. Temperature of that day. It doesn't show to be correct when we look at the data we got from the client's portfolio, but again, it doesn't make much difference. So what I have tried it, calibrated with the average temperature the previous 6 days as the initial temperature for the tank. Yeah. Next one, please. Again, this is a correlation between the inside temperature and the mathematical formulation we regress from the measured data. Yeah, next one. Wind speed, as I said, it's very important because we lose heat due to convection. On a zero wind speed, HC, heat transfer coefficient is about 10, but when it is, I think it's about 16, it's very sensitive, it goes quite up. So if it is windy, our temperature would be much lower because we lose heat from the wall to the surrounding. Yeah, next one, please. Thermal properties, again, thermal conductivity of saturated concrete is about 1.4 joules per meters per second per C, but it can increase to about 2.2 for hydrating cement like wet concrete. The specific heat doesn't change much. It varies from 900 to 1000. And the surface absorptivity factor, as I said, is very important. On a black surface, like all concrete, is 0.9. So if S is the incident solar radiation from the sun, 90% will be absorbed. Whereas a white surface, only 35%, other 65% will be push back as reflect back to the surrounding. Yeah, next one, please. Yeah, finite difference model. So we got inside temperature, so solar radiation, ambient. Then we can do a finite difference. I am prejudiced towards finite difference, but there are finite element modulus as well. Yeah, next one. As I said, this you saw this diagram earlier, so we are going to mathematically model it. Next one, please. So system, we got on our right, we got all the incident solar radiation things go out of the thing QC, and then the water remaining at almost constant temperature. Yeah, next one, please. This is a fixed second law of heat transfer, and similar is for groundwater, similar is for diffusion of moisture, very similar. And we need to mathematically model it. In my case, using finite differences. See, on your right, we got density and specific heat, C. As I said, if specific heat is C is 0, because to raise the temperature of material, we don't need much heat, that curve become linear. So that's one thing. So when it becomes linear, it's known as steady state. That's what they sometimes only teach students steady state. So if you go T1, external T2, they draw it with a line. But it's not the case when you go to unsteady state. Yeah, next one, please. So this is a finite difference discretization, n plus 1 nodal points and n layers. Yeah. Next one, please. So I'm just going through this one very quickly. And these are how you do mathematical balance in a finite difference. And some of the papers, 1990, I wrote got this formula. Yeah, next one, please. Next one. So this interior node, that's the equation, how it looks like. And external surface, this is how it looks like. So just there are two methods in finite difference. One is implicit, that is moving forward. So we had to have an n by n matrix to be solved. But we got explicit, it's a backward substitution. So you can do on a spreadsheet or hand calcs without any iterations, nothing, but you had to select a time step slow, otherwise it become numerically unstable. I use implicit because I got the program written a while ago, but if I am lazy, I do it on Excel spreadsheet. Yeah. Using explicit scheme. Yeah. Okay, next one. Next one. Yeah. I write those formula for external and internal nodes, and I get this matrix. I use a direct inversion method, but some people don't like scaling computer. But nowadays computers are so powerful. 50 by 50 matrix is solved in probably less than half a second. Yeah, next one, please. Yeah, this model I just thought put in some. This model we calibrate use real prototype concrete slabs heated from one side with a cooling, circulating water cooling jacket on the other side. And then they were tested for bending moments and axial forces. And these were published myself and Nigel Priestley in 1998 and 1999 in the American Concrete Institute of Structural, Yeah, next one, please. Next one. Yeah, so this is a schematic representation of the cooling jacket. You got heat lamps, infrared, on one side and the cooling jacket on the other side. When we measure temperature gradients as well as restraint forces, need to restrain them to calculate bending moment and axial forces they induce. Next one, please. This instrumented slabs at the University of Canterbury. I and the technician did this, all the manufacturing, still everything day and night. Yeah. Next one. Yeah, this is measured as well as finite difference program. See how, it's reasonable matching. But if we massage the numbers, we can get 100% accuracy, but that's not the purpose. Yeah, next one, please. And these are the induced bending moments on the given curvature. Again, this is available in the ACI structure. Yeah. Next one, please. Now, all this is good. So for Sydney, we did a lot of calculations of few days and various tanks, various conditions to come up with nonlinear gradients. Yeah. So I will present those ones very quickly. Next one, please. So 3 scenarios were considered: the day with maximum recorded global radiation Q, and maximum ambient temperature day, minimum ambient temperature day for 45 years records. Yeah. We didn't want to do probability. We just want to get the maximum and make sure the things are a little bit conservative. Yeah. Next one, please. Yeah. So summary of the finite difference analysis, critical maximum and minimum temperatures gradients. Yeah. Next one, please. Yeah. Water tank and acid phase digester 2 have the similar temperature gradients. When we said acid phase digester 2 is, it comes to acid phase digester 1, it's the first one. It's the stabilized things, so temperatures are not as close as to the ambient, exposed previously. So only given the water tank ones. And so this is the day with Qmax. And the value we got dt max is 30 degrees, and the wall thickness is here 350, 250. So you can see the nonlinear gradient becomes critical with increased wall thickness. Next one, please. So these are some sample charts. I just want to give this is a winter day. Again, minus T minimum ambient with -6. And again, here we get -11. See temperature difference. You can see nothing is linear. They all tend to be nonlinear at high wall thickness. Yeah. Next one, please. These are the digest phase 1. They got different behaviors. And again, you can see the summer temperature gradients. They have become nonlinear as the thickness becomes larger than 200. Yeah, next one. Similar, this is winter. The temperature gradient reverses. It's not increasing, it's dropping on the external surface. You can remember New Zealand, say, -20 degrees here for -12. So Sydney is different from Christchurch. And that's what I said, it's very location specific. Yeah. Next one, please. Yeah, these are gas phase digester. That's what I said, they are internally heated 36 degrees from day number 1. And one scenario I didn't present here, we look at first filling. When you fill it first, it's a thermal shock to the tank. So last thing you want to do is crack the digester and tell the owner it's a good luck we crack your tank. Yeah. So this is a long time since filling. Again, DT max here is 35 degrees, or New Zealand 30 degrees. Somebody apply a digested. It's an unsafe design. Yeah, next one, please. So the maximum ambient temperature is a similar day. Similar. I mean, this is a winter. So again, different curve. Inside remains at 36, while the outside drops to, I think that day, outside temperature is -4, I think. Yeah. Next one, please. -6 that day. So I just want to say east facing versus west. What in the morning we get east facing won't get the solar radiation, but the ambient temperature is lower, be in early morning. But when it goes to the west, probably the same solar radiation, but we got a high ambient because it has heated up. But still the difference is about 4 degrees. Sometimes not worth worrying about 4 degrees when we know all the uncertainties involved. Yeah, next one. All that is good, but every engineer can't sit and whatever.
Sorry, there was some crash. Give me one, please.
Okay. You may have reboot. Be on time. Yeah. Yeah. So as I said, not every engineer can do finite difference. I get young guys who can't differentiate sine theta. Looking is when I said that looking at my face how to do it, I need to find the Google. But so for that reason, we try to develop a nonlinear model, at least for the summer, because it's very difficult to do it's a position dependent, day dependent, operational dependent, but at least for summer, which is the critical one for tank design, to give this nonlinear gradient which cover all the wall thicknesses. And with that, the tendency would be design won't be that conservative, but it is almost similar linear when it is about 175 millimeters, but it becomes nonlinear for higher thicknesses. So with higher thicknesses, it will provide economy in the design as opposed to just cursorily using New Zealand linear gradients. Yeah. Next one, please. You copied it correctly? Yeah. So this is a formula. So you can see when TW is a wall thickness. When wall thickness is 175 millimeters, it basically become linear. But TW divided by 175 become 1. I think there should not be that minus in the front of 1, but that's fine. Because we had issues with this one copied from Word to the PowerPoint presentation. So this is valid for TW, any wall thickness greater than 175. I tested it extensively. I spent about 1 week just playing around with the model. Okay, let's go to the next one. So this is a 250 millimeter wall. The linear one is a New Zealand, 30 degrees. And then the black one is the dark blue one is the finite difference, which I said earlier. Then the orange one, yeah, is a parabolic profile, which is closed with the finite difference. And again, they tend to be linear. So if I put 175, all those three curves become linear, similar to the New Zealand standard one. Yeah, next one. So when it becomes 600 millimeter, it matches very closely with the finite difference calculation done. So no need to do finite difference. You can use this formula to get your nonlinear gradient. You can see just looking at the diagrams how conservative it would have been if what we engineers tend to do without knowing the limitation of that gradient. That is, they are applying only for thinner members, applying to everything. You end up with crazy design. As I said, sometimes bumblebees can't go through. And contractors say, oh, we have never seen that much reinforcement in some of the designs in the past. Yeah, next one. Again, yeah, these are as I said, I didn't want to go into detail into stress calculation, but I get that lengthy formula in the first or second slide. You can see this equivalent temperature from the finite curve fitting and finite difference. The top one is the AS37 about 30 degrees, and then the curvy one, orange color, is the actual temperature, nonlinear temperature distribution. Then the dotted line, linear one, is the equivalent linear. So if you look at it, that goes from 15 degrees to -5. So 15 plus -5 average is about 10 degrees. When we compare with New Zealand, average is 15. So it's a significant cost saving, about 50%. And the sort of dotted non-linear one are the primary thermal stresses. As I said, even unrestrained, there will be thermal stresses due to non-linear gradient. That's not the case with linear gradient. Next one. I think that's the end. Yeah, so these are the findings. Inside temperature of water, tanks and digesters were correlated in our study, but it's very important to get that in order because you can't mathematically model it because the water and sludge comes in and go out. It's an operational thing. With solar radiation in summer, significant temperature nonlinearity exists. This highlights the conservatism in using New Zealand 3106 gradients for thicker walls, say greater than 200 millimeters. GPD3, that gas phase digesters, it's not a water tank. All the people apply the same temperature gradient because it's got a very unusual operational requirement, 36 degrees, maintained artificially throughout the day. And if not careful during the first heating, it will have a thermal shock. I was involved in a pulp and paper tank where they put 70-degree hot water into the tank and it cracks as people were watching it. It's a thermal shock, so I had to be careful. Next one. End?
Yes, that's all.
Yeah, that's it. So it's a long journey, but I just want to give you insight. It won't make you a design engineer, but at least give an appreciation of what other standards around the world are doing, and they make much sense rather than using European norm. What do you call EN 1990, probably in Sri Lanka. It gives deemed to satisfy criteria like minimum, extra steel or whatever it is, and they don't make sense. Any questions?
If you have any questions, you can ask by unmuting yourself, or you may send to the chat box as well.
Don't ask why Kotmale gates were open suddenly. No, I won't be answering here. In saying hello English doesn't matter. No questions?
So they have several temperature models we have taken into consideration in the presentation. So is there anything like what is the most accurate model or something? Any for that, or it is just the practice and understanding whether
Which
each model
one? Is
is
a
matching?
finite difference or
Yes,
which
finite.
model? So
Yes,
yeah,
yeah.
there are programs, but you have to be careful. I had to be, anyway, I'll mention the package. Strand 7. Strand 7 can't take uniform. When you put temperature, it only does a uniform, but there's no uniform temperature when it's exposed to solar radiation. So people do. I was involved in the big wastewater treatment plant. The answer, the calculation by the designers don't make sense. I was independent verifier. I self-verified. Something is wrong. It doesn't make sense. No, our model is good. You are wrong and all that. But then I said, come sit with me. I said, they sat down with me. We do the calc program. Doesn't, it's like a black box. So you put a black box, put something and so if rather than, I told the client, rather than wasting time, if I were you, I buy beer and drink it. You get 10 cents back from the recycling the can. So you have to be very careful. It's much better to do hand calc. So as I said, some procedures, you get a feeling of what you're doing.
Okay, sir. Thank
For
you.
like solar radiation, I went through the methodology, but there may be some simple pack software, piece of software used by the solar panel industry. But again, as I said, 40% coming from on a tank, or 40% of solar radiation come with the reflected back from the surrounding. So solar panel is not horizontal, vertical, so you can miss that part.
Okay, sir. Thank you. And any more questions from
I
the
can't hear,
audience?
Increase.
Yes, any more questions from the audience?
Can somebody tell me how do they design water tanks in Sri Lanka? You calculate the crack width? You calculate the crack width, or you limit the steel stress? No.
We go with the crack width calculation is considered.
Yeah, but as I said, that's what I want to get the answer from you guys. Crack width, if I can get 3 equations from the world, I can give you any answer you like. So because crack width has a very big coefficient of variation, or called standard deviation, up to 30%. So that's what we don't do that in our codes. We limit the steel stress so that we don't have disputes. One would say my formula, crack width calculation formula is good, better than anybody else. Americans say better than UK say better than anybody else. And that's a problem. For as an example, I think it's still Sri Lanka British say maximum crack width, say 1.1. What's the maximum? Maximum to the lawyer is maximum. They can't say it's maximum 0.1, say, but it went to 0.1 to lawyer say, no, you said maximum 0.1, it's 0.1. So we don't even use maximum, we use characteristic crack width, 95% percentile. So still we got 5% upslave if a lawyer try to jump onto your throat. And formulas give mean. All the British formulas give mean crack width. So how do you do mean to characteristic? So normally standard variation is 0.3, I think. Mean plus 1.63 times 0.3 times average is a maximum. So 0.15 is normally 0.18. When it 0.15 mean is about 0.18 max. So when they teach engineers, they have to be very careful at university what they teach. Otherwise, the lawyers will fry them in open frying pan. Things get wrong. Probably not in some jurisdictions. If people meet with accident, only policemen going to the jails. And where I work, some diesel one, engineers do the wrong things. They can lose a hand. They chop it off. So, so every time you do calculations and design, or if you're in charge of something, you got a duty of care. You can't hide behind the standard or standing order and said, I did this one because that's what the standing order said. It doesn't work that way.
Okay, and so there's one question. Is there a role of admixture or additives in concrete here from design perspective?
To temperature lowering?
Yes.
No. You can put, like dams, I do a lot of concrete dams, you do artificial cooling. But only one digest in Philippines I was involved because we had to have a lot of cement due to the durability issue. So we had to use artificial cooling on the SBR, sequence biological reactor, to cool it down, otherwise it will crack. Admixtures, temperature, again, I'm very skeptical about admixtures. Get good concrete mixes and pour it well, cure it well. It will go for 120 years. This admixtures most of the time is a waste of money. Of course, fly ash and slag, silica foam, they have a role because they are cementitious material, but they have low heat generation due to hydration and better permeability values for diffusion. But other things, available in the market, just as I said, buy beer and drink it, you get 10 cents back. That's what I do. Any other questions? We got 20 minutes. Do they have pre-stressed tanks in Sri Lanka? Probably. Chinese contractors, they are good with, and Japanese good with pre-stressed tanks. So with this, if there are engineers or graduates want to do research or something and locally, they can do. It's not expensive. You get most of the things. You get time. Just the time in front of a computer is the investment you need to run the models and develop gradients for Sri Lanka, which doesn't have a winter, but it will have high temperatures. Nothing?
There are any more questions, you can unmute yourself and ask, or you can send to the chat box. Looks like there are no more questions.
Yeah. So we had 75, only 3 questions.
No, we had 100 cards, you can say. Yeah.
Anyway, that's okay. I think it's good.
And there's one question.
What is it?
Can you just elaborate the questions and clear for me? Maybe he's asking the tanks with spherical surfaces, whether there are any radiation calculations.
Which one?
tanks with spherical surfaces.
It's like a dome, roof.
Yes, maybe like a dome. Yeah.
Yeah, can do, but first you have to define the temperature gradients, and either you can do the charts or you can input that to a program. I don't know, SAP or Strand 7, that sort of programs. But first you have to get the gradient. That's the important part. Input is more important than analysis, other way around. But now most engineers first try to do analysis before understanding the problem, because universities mainly make them running computers than learning calculations. And if you look at, as I said, serviceability calculation is an elastic calculation. You don't do ultimate. So I don't think any more, even here, universities don't use elastic theory, working stress calculation, because I don't know the reason. Probably the employers like to use it, do ultimate, but serviceability is usually the problem, causing projects going belly up. I was in only diesel, it went belly up within 2 months. The inaccessible filter chambers cracked, and you can put a pencil through the wall because the specification never said anything about what's the maximum placing temperatures. Contractors are not going to save money. They just from the clinker and pour concrete and said, this is what you asked for and you got it. And they got 4 trucks injecting epoxy for about 2 months.
Are there any more questions? We will. Looks like there are no more questions. So then, thank you, sir. And I would like to invite the Secretary of American Society of Civil Engineers, Sri Lanka section, Engineer Dr. Pagit Vijayasekara, to do the vote of thanks.
Good evening to you all. On behalf of the American Society of Civil Engineers Sri Lanka section, it is my great privilege to propose the vote of thanks for today's jointly organized webinar on design against ambient thermal effects on concrete. First and foremost, I wish to express our sincere and heartfelt appreciation to our distinguished resource person, Engineer Dr. Nihal Vitarna, for delivering an exceptionally insightful and technically enriching presentation. Dr. Vitarna's extensive professional experience, pioneering research on the thermal behavior of concrete structures, and his valuable contributions to international standards such as ASCE 3735 and ASCE 3106 have greatly enhanced our understanding of this important subject. We are truly grateful for his time, dedication, and willingness to share his expertise with us. Secondly, I would like to extend our sincere gratitude to Engineer Dr. Kamal Laksiri, past President of Institution of Engineers Sri Lanka, Governor of ASCE Region 10, Engineer Kosala Kamuradeniya, President of ISL, and Dr. Densil Lokuliyana, President of American Society of Civil Engineers Sri Lanka section, for his guidance, leadership, and continuous support in fostering professional excellence and collaboration between our institutions. We also wish to express our appreciation to Engineer Mrs. Kamala Gunawardana, Vice President of ISL, for her encouragement and support towards professional development initiatives such as this joint technical webinar. Our special thanks go to Dr. Banduka Kuruppu, Technical Event Coordinator of the Civil Engineer Sectional Committee of ISL, for his valuable efforts in coordinating and supporting the technical arrangements of this event. We sincerely thank the Chairman and members of the Civil Engineer Sectional Committee of ISL for partnering with the American Society of Civil Engineers Sri Lanka section to successfully organize this timely and important technical session. This collaboration reflects our shared commitment to advancing civil engineering knowledge and practice. I would also like to acknowledge the dedicated efforts of the organizing committees of both institutions, as well as all those who worked the scenes to ensure the smooth and successful conduct of today's webinar. Finally, we extend our heartfelt appreciations to all participants, including our international participants from the ASCE global community, for joining us today and contributing to the success of this event through your active participation and engagement. Once again, thank you all for being part of this valuable knowledge sharing platform. We look forward to your continued support and participation in future programs jointly organized by ASCE Sri Lanka section and Civil Engineering Sectional Committee of ISL. Thank you and have a pleasant evening.
Thank you.
Thank you. Thank you. Thank you, sir.